Okay, we're now at section 17.6, electrical energy and power. Let's get started. All right, let's look at the energy transfer in a simple circuit consisting of a battery and a resistor as shown in the figure. The chemical energy stored in the battery is transformed into kinetic energy of the charge carriers. This kinetic energy is quickly lost as a result of collisions between the charge carriers and fixed atoms in the conductors, which causes the temperature of the conductor to increase. Imagine following a quantity of positive charges delta Q through the circuit. We'll start at point A, there in the left side of the figure. We'll start at point A, which is a reference point that is grounded, and its potential is taken to be 0. The little triangular symbol at the bottom, that's the ground symbol. As the charge delta Q moves from A to B through the battery, the electrical potential energy of the system increases by the amount delta Q delta V, and the chemical potential energy in the battery decreases by the same amount. As the charge moves from C to D through the resistor, it loses this electrical potential energy during collisions with atoms in the resistor. In the process, the energy is transformed to internal energy corresponding to increased vibrational motion of those atoms. We will ignore the very small resistance of the interconnecting wires, so no energy transformation occurs for paths B to C and D to A. When the charge returns to point A, the net result is that some of the chemical energy in the battery has been delivered to the resistor and has caused temperature to rise. Okay, the charge delta Q loses energy delta Q delta V as it passes through the resistor. If delta T is the time it takes the charge to pass through the resistor, the instantaneous rate which it loses electrical potential energy is given here, where I is the current in the resistor and delta V is the potential difference across it. So the limit as delta T approaches 0 of delta Q over delta T times delta V is basically I delta V, because the limit as delta T approaches 0 of delta Q over delta T is current. Okay. Of course, the charge regains this energy when it passes through the battery at the expense of chemical energy in the battery. The rate at which the system loses potential energy as the charge passes through the resistor is equal to the rate at which the system gains internal energy in the resistor. So we can write the equation for power shown here. Power equals I times delta V. This equation can be used to determine the power transferred from a voltage source to any device carrying a current I and having a potential difference delta V between its terminals. Since delta V equals IR for a resistor, we can express the power delivered to the resistor in two other ways. When I is in amperes, delta V in volts, and R in ohms. The SI unit of power is the watt. So we can get, so we have three forms. Power equals I times delta V, power equals I squared R, and power also equals delta V squared divided by R. Okay. We often refer to the power delivered to a conductor of resistance R as an I squared R loss. Keep in mind that these equations apply only to resistors and not to non-ohmic devices. Such as light bulbs and diodes. The unit of energy used by electric companies to calculate consumption, the kilowatt hour, is defined in terms of the unit and the amount of time it's supplied. So 1 kilowatt hour equals 10 to the 3 watts times 3,600 seconds, which is equal to 3.6 times 10 to the 6 joules. 1 kilowatt hour is the energy converted to consume or consumed in 1 hour at the constant rate of 1 kilowatt. So 3,600 seconds is 1 hour, 60 seconds in a minute, and then 60 times 60 minutes in an hour, you get 3,600 seconds in an hour. Okay, this ends our discussion of electrical energy and power. We're going to skip the section on superconductors. You're certainly welcome to study it, but I won't make the class responsible for any of the content. Next, we'll discuss section 17.8, electrical activity in the heart.